Welcome to another video. In this video, we cover one of the most practical and widely used concepts in statistics, linear regression. Linear regression helps us understand and quantify the relationship between variables, allowing us to explain patterns in data and make informed predictions. We will see how regression goes beyond drawing a best-fit line and becomes a powerful tool for reasoning under uncertainty and supporting real-world decision-making. The Space Shuttle Challenger accident in January 1986 occurred because the rubber O-rings used to seal joints in the solid rocket boosters lost their ability to seal properly in extremely cold conditions, allowing hot gases to escape during launch. Before the accident, engineers already had data linking O-ring damage to temperature from previous launches. The problem was not a lack of data, but the lack of a clear statistical model to connect temperature to the risk of failure. Here, we can see why regression analysis matters. Regression provides a way to systematically relate one variable to another and use that relationship to assess risk. In this case, regression could have been used to relate ambient temperature to the likelihood of O-ring failure and to evaluate how dangerous the unusually low launch temperature was. Even without complex analysis, a regression-based view would have highlighted that the launch conditions were far outside the safe range suggested by prior data. This example shows us that regression is more than a mathematical technique. It is a tool for understanding relationships, making informed decisions, and preventing costly or catastrophic outcomes. Many problems in engineering and the sciences involve a study or analysis of the relationship between two or more variables. For example, the displacement of a particle at a certain time is related to its velocity. Let d0 be the displacement of the particle from the origin at time 0 and v be the velocity. The displacement at time t equals to d0 plus v times t. This is an example of a deterministic linear relationship because the model predicts displacement perfectly. However, in many situations, the relationship between variables is not deterministic. The collection of statistical tools that are used to model and explore relationships between variables that are related in a non-deterministic manner is called regression analysis. Because problems of this type occur so frequently in many branches of engineering and science, regression analysis is one of the most widely used statistical tools. In simple linear regression, we present the situation in which there is only one predictor, also known as independent variable x, and the relationship with the response variable, also known as dependent variable y, is assumed to be linear. Although this seems to be a simple scenario, many practical problems fall into this framework. Let's go over a real-world example together. Here, a chemist is working on producing oxygen through a complicated chemical experiment. The chemist knows that purity of oxygen produced in the procedure depends on existing levels of hydrocarbon in the raw material based on 20 experimental runs that the chemist has already executed. We want to explore whether we can use these prior 20 data points to define a linear regression model that can estimate the purity of oxygen to be produced prior to running the experiment if we use raw material with a known level of hydrocarbon. Here, we can see the chemist's observations from his first 20 attempts. After closely inspecting the scatter plot, we can see that first, no lines or even simple curves pass through all points. Second, if we produce a line that best explains the behavior of the data, these observations lie scattered randomly around that line. Considering these remarks, it is probably reasonable to assume that the mean of the random variable y, which represent the purity of oxygen, is related to x, which is the existing levels of hydrocarbon in the raw material by a linear relationship. This means the expected oxygen purity given the existing level of hydrocarbon in the raw material follows a line. To summarize, we know that the purple line does not pass all data points. So, we cannot claim that y equals to beta 0 plus beta 1 times x, where beta 0 represents the intercept of and beta 1 represent the slope of a typical line. As the line is missing so many points, we claim the y equals to beta 0 plus beta 1 times x plus error. We also make some assumptions on this error term that it follows a normal distribution with mean 0 and a fixed variance. This assumption is very important, as it shows the expected value of our model is equal to the fitted line and its variance is fixed. This means if we know x, the level of hydrocarbon in the raw material, We can plug it in the fitted line and report the most likely value, not the exact value, most likely value of oxygen purity as beta 0 plus beta 1 times level of hydrocarbon in the raw material. By assuming that the error term follows a normal distribution, we are implicitly assuming that the response variable also follows a normal distribution centered at beta 0 plus beta 1 times x with a constant variance of sigma squared. Suppose the best fitting intercept and slope for these 20 observations are 74 and 15, respectively. This means that when the level of hydrocarbon in the raw material is 1, the purity of oxygen follows a normal distribution centered at 89. We get this 89 by adding 74 to 15 times 1. We would therefore report 89 as the most probable, or expected, value of the oxygen purity. However, once the oxygen is produced, its purity will not necessarily be exactly 89. This is because the purity is a random variable that follows a normal distribution centered at 89, and the theoretical domain of a normal distribution extends from negative infinity to positive infinity. In practice, this does not mean extreme values are likely. Most observed purity values will fall close to 89, with the likelihood of values farther away decreasing rapidly depending on the size of sigma squared. As a result, while different purity levels may be observed from batch to batch, they are expected to vary only modestly around 89, rather than deviate substantially from it. When the hydrocarbon level increases by 1 unit, the expected oxygen purity increases, but individual production outcomes do not exactly match this expected value. Instead, the observed purity values vary around the predicted mean response and tend to remain closer to the typical purity level rather than exhibiting extreme deviations. This idea is closely related to the historical origins of linear regression. The term regression analysis was first used in a study of the heights of fathers and sons, where a least squares line was fitted to predict a son's height from his father's height. Researchers observed that when a father's height was above average, the son's height was also likely to be above average, but typically not by the same amount. Similarly, when a father's height was below average, the son's height tended to be below average, but not as far below. In both cases, the son's height tended to move, or regress, toward the overall average. Just as sons' heights were not as extreme as their father's heights, the observed oxygen purity values regress toward the average purity predicted by the linear model. Thank you for watching. I hope this video was helpful, and I look forward to seeing you in the next one.